Okay, so it is 4 o'clock, so let's get started. Okay, hello everyone, and welcome to today's webinar. So my name is Ignacio Payaza Forteza. I'm a professor of structural engineering at the Universidad Politécnica de Valencia in Spain. I've been working on bridge fires in research and practice since 2009, and together with Stefan Smigrowski, who is the speaker today, we started a task group within IABSE to address the design of bridges against fire hazards. So I guess you know, but in any case, a short reminder, IABSE is the International Association for Bridge and Structural Engineering. It was founded in 1929 and is a uh, world spread association that brings together structural engineers, academics, practitioners, and any professional who is committed to advance the art and science of structural design. So within IABSE, there are several commissions, and there is Commission 1 that is focused on structures and that has several task groups. And one of these task groups is Task Group 1-2, which is aimed to improve the bridge resilience to fire events. And this seminar is part, or this webinar is part of the activities of this group. There will be 2 webinars. This is the first one, and I want to tell you that the group is open, so you can get more information and you can join also the group if you send an email to the address that will be written in the chat of the webinar. Okay. I also want to point out that if you have any question, please feel free to write them down in the questions and answer part of the chat. Sorry, not of the chat, of the Zoom environment. And also before presenting Stefan, I want to highlight 3 major upcoming IABSE events. So in 2 weeks, we will be celebrating the symposium in Tokyo between May 18 and May 21. Then at the end of August, we have the symposium, the Congress in Ghent. And finally, in a little bit less than 1 year, at the end of April, we will have the Copenhagen Symposium. And here the submission of abstracts is still open. So if you want to submit an abstract, I strongly encourage you to do so because it is a very interesting opportunity. It's a very nice network, and I really enjoy being a part of this organization. So I encourage you to join the association and of course to attend the seminars and the symposium. And then just to end this introduction, I want to introduce you to a speaker. So Stefan is a highly accomplished structural engineer. He graduated with honors from the Warsaw University of Technology in Poland, and he has gained extensive international experience because he has been working in major engineering firms in Poland, in Austria, and in Canada. He's currently working in an occasional way as a specialized consultant with Sigma Plus, one of Canada's leading engineering firms. And his technical expertise covers a wide range of structures. It includes bridges, tunnels, industrial facilities, seismic retrofitting, and he's particularly interested in fire engineering and life cycle engineering. And he has several publications on these topics. Stefan, he's also the vice chair of Task Group 1-2, and he's very committed to IABSE, so he's leading also several other task groups like the 1-5 on performance-based design and 1-14 on holistic fire engineering. And I think that he will bring a unique perspective to this topic, and I hope that you will enjoy the presentation, and the floor is yours. There will be time for questions after the presentation. So thank you, Stefan. Go ahead.
Yeah, thanks much. So welcome to this very first webinar of the task group 1.2, which has been divided in 2 parts. So we are in the part 1, was prepared by, as mentioned by my colleague, by both of us, and is focused on the importance of bridge fires and the why we should address this aspect on the reliability of bridges exposed to fire, dealing with fire hazard and fire injury related to structure. Part 1 it includes introduction to the theme, examples of bridge fires, and words about response to fire. Part 2 will be dedicated to the design for fire bridges, risk analysis, as well as dealing with fire hazard, which is a very important aspect for getting this approach. And closing remarks. That's going to be in for about 1 month, in the month of June. To be precise, I think it's 5th or 6th. So let's go to the for first part, and I have to mention that this been prepared, for sometimes before, and so we refer to the publication of which are about 10 years, but still very, very appropriate. And the first is an FPA published in 2011. For reporting fires in the USA, about 200,000, which have happened, and for most of them on the rural roads and driveways, and half on highway streets and commercial roads. Those for second half represents about 80,000 fires, and bring us to every 6.5 minutes fire that happened in this period. Another reference is the survey done by USA as well, reporting causes on bridge failures based on the reasons. So we have most of them hydraulic collisions, follow overloading, deterioration, and fire represents about 3% of the collapses that been reported. But before earthquakes, and why I underline why, other causes like ice, fatigue in steel, design problems, etc., each of them represents less than 1%. Now, with respect to fire due to fire, the fire earthquake, we have in this period 20 over 50 due to fire and 19 to earthquake. So another for reference is a technical paper for reporting bridge failures in the period of about 30 years, where fires also mentioned as one of the reasons, and compared to wind and earthquake, and I will say why those are important if 1 minute, they represent a high number. So summarizing, bridges are more likely to collapse due to fire than earthquakes and wind. However, wind and earthquakes, as well as ship collisions, are reflected in actual codes and standards for bridges, but not fire. So let's go to the examples of bridge fires. Those are for detail in the analysis of causes published in 2016 by the American Society of Civil Engineers, according to 5 levels. That very, it's about 20 cases we show here, and with different level of damage and different scenario of fire. And these levels are from 1 to 5, the very, very superficial to the complete collapse. The level 1 is defined as a minimum damage, not affecting the structure of the bridge. If it's like superficial and it's without any important impact on the performance of the bridge. Slight damage, which requires some repairs. This could be concrete spalling, but not, for exposed rebar. Blackening of concrete, slight damage to steel beams. Partial damage required a replacement on some structural elements. Level 4 is massive damage, considered damage but not collapse. However, due to the extension of deterioration, bridges are damaged and should be demolished. And structural collapse where the total collapse take place. So the two last level 4 and level 5 could be qualified as total loss of the bridge. So let's go to this list. You have it's divided in 2 parts with the data, and we'll follow you according to the in the chronological way. And cause of fire, bridge material damage expression would be showing this in each case. We have 22 cases, and let's start with the first one. It's in Alabama, close to Birmingham, a case of gasoline tanker which overturned and started fire under the bridge. The bridge was built as a composite deck, and damage level you can see on the photo. Bridge collapsed due to this event. Die Wildtalbrücke in Germany is a very interesting case. The fire started on the highway, and the tanker has fallen. And you see the fire on the left side of the screen is well below the deck structure, and the damage is shown on the right side below. You see the extent of damage which required partial replacement of the structure. It's qualified as level 3. But I'd like to underline, the effect on heat of this fire on the structure, which is well above the burning of tanker. Another case is reported. It's less relevant in terms of fire, but it's with a case of bridge in Greece, where was loss of cables due probably with lighting. It's not certain the cause. Another one is Queens Expressway and Roosevelt Avenue intersection in New York City. Was a crash of tanker under the bridge. Bridge was under construction. Only steel girders were in place, and bridge collapse, total collapse, bridge level number, damage level number 5. Mescala Bridge in Mexico was a fire of truck carrying coconut. Collided with buses, and was loss of cable and limited to damage to adjacent cables. Relevant, but in terms of impact on the cable, it should be underlined that it's part of any design approach to cable stayed bridges or suspended bridges, impact on the supporting structure. Another following case is the MacArthur Maze Bridge in Auckland. Auckland, it's on the link, the highway between Auckland and San Francisco, due to the crash of a gasoline tanker under the bridge. You see the images from it's happened in the night, and the results is here. So very important, because it was a connection between these two major cities. And on the right side, you see San Francisco is the upper part. The bridge is located in Auckland. So a 50 meters long section collapsed due to this fire. Bridge was built as steel girders with a concrete slab. Another case from Detroit. Again, a gasoline tanker struck for an overpass. Complete collapse took place, as shown in the photo on the right side. Another case reported in this survey is less relevant, but still of some importance. I think it was fire of ties. It could be repaired, of course, very easily. Another case of coming from the U.S. Montebello, California. Another gasoline tanker fire under the bridge, and this bridge was built as concrete girders and concrete slab. General spalling occurred, and the damage to the rivers was extensive. So even if the bridge didn't collapse, it was demolished due to the extent of damage. We're in Germany, Dormagen. Fire under the bridge. It wasn't done. This case is very interesting because it was a storage of plastics below the bridge, and it caught fire and damaged very, very extensively the structure. So the bridge was built as thick concrete slab, and due to the general spalling in the section of fire, the bridge had to be demolished. A very interesting case of the Mathilde Bridge in Rouen, France, where we saw the photo on the right, the fire under the bridge on the shore. The fire, however, the incident started on the bridge, where the tanker overturned, caught fire on the bridge, and the fuel, the tanker remained on the deck, but the fuel spill reached trucks parked under the bridge, which caught fire as well. So the fire was basically, the damage of fire was due to the trucks parked underneath, and the extensive the smoke is very, very, very appealing. The result you can see here, the section where the trucks parked under the bridge, it's a severe deformation and damage to the steel structure. And part of the bridge had to be demolished. Coming back to the United States, Pennsylvania, there were two bridges involved in the fire, diesel tanker. Once again, we have dangerous goods. I mean, very, very, very high combustible load. And bridge had to be demolished. One of the bridges, the lower bridge, could be repaired. And so it's again steel girders and concrete. The extent of damages due to this fire was very important. Queensboro Bridge in New York City was a fire of the trailer, and with a light impact on the structure, two stringers on the upper deck were severely damaged and deformed. Overpass in Kano, it's another case where there was some use of the space below the bridge. Gas cylinders exploded underneath in the shantytown, and you see the results is complete collapse. Steel structure, I mean, standard one composite deck, steel, concrete, and steel beams and concrete slab. One column and three sections of bridge collapsed due to this fire. We are in California, Rancher Road in Esperia. It was a fire caused by during construction, accidentally initiated by workers, and wooden formwork took fire, and everything what was in place had collapsed. Patonsville in Tennessee, again gasoline tanker collided with the pier and exploded. There were two overpasses, one with concrete bridges, a second one was under construction. Both bridges were demolished due to the significant spalling concrete to severe the formation of steel girders. The Wyszynowski Bridge over the Vistula River in Warsaw, my native city, was caused by the fire of dismantled wooden service decks started on the shore. So you see on the left side below is the fire under the bridge, and the photo on the right side show the fuming deck during this fire. And the result of this heat, you can see on the right upper side, it's quite extensive. Everything else, steel was so heavy, they heated that the asphalt was in the state you can see on the right side above and below. The deformation to the steel beams were extensive, and the bridge had to be completely demolished, total replacement. Another case of tanker, this one ethanol, not it's also very, very high high level of combustible load involved in this fire. and the structure was concrete, and it's a very good example to see the effect of spalling and the impact on the rebar, which was broken and fell. Bridge was demolished after this fire. Train viaduct in New York City. It's another case interesting, because of the material stored under the bridge, or any other use. The fire started by fueling of the generator, and it was spread then on chemicals stored in the garden nursery in operation. So it was quite important fire with the impact of the structure. We can see on the right side or one column, but it was damaged, level 3. But the use of the space on underneath the bridge, it's very important aspect in the approach to the design and assessment of risk related to the risk of fire. Now we are in my actual city, Montreal. Was a fire, very, very, very impressive one on the highway crossing the city center, where diesel tanker collided with 3 cars, and that's what happened. But the damage were very limited. The fire was on the bridge, so it was local for cosmetic intervention afterwards. There was no structural damage, no structural problems. Bridge in Pittsburgh, Pennsylvania, during which follow some not well performed works work by people working on this bridge, cutting the stall, and started with the fire of plastic ventilation and pipes and construction traps. The damage level was unknown. And last on the series, the bridge in San Rafael. It's north of San Francisco, where a trailer of soil caught fire after slamming into the guard line on the lower deck, and caused slight damage to the bridge, which was reopened shortly after. So after this overview, we put the red for color on the right side, to show in this series of over 20 cases where the total collapse took place. It was quite extensive, and all these bridges are considered, so even less relevant for the problems. And what was the economic impact? It's not something it didn't discuss in every case, but the fire of the bridge in Auckland. We have data, and it's very interesting to compare the reconstruction cost with the economic impact. The reconstruction was about $9 million in the dollars from 2007, and economic impact represented 26 days of $6 million per day, so 70 times reconstruction cost. So economic aspect is very, very important, depending on the category of the bridge. And it is for importance in for road network. That's an aspect should be carefully evaluated and considering the approach in terms of design and risk factors. So some observation arising from this review of over 20 cases, fire caused by gasoline tanks are most devastating. It's not natural because that's the potential for of the fire load is enormous, and the speed of the fire is very important. And of course, should be underlined that the structure is in direct contact with the flames, then the damages are more important. But we have to be careful. The case of Wittelbrick in Germany showed that even the big space of free with a free ventilation exposed to air doesn't necessarily mean that the bridge is safe. Most of their business will be with steel girders, which we'll discuss later in terms of vulnerability of type of material to the fire. For any for other material like scaffolding, form, etc., built of wood represents risk. And spaces under bridges are very important aspect in terms of risk for risk factors. With this, there are 3 or 4 cases, where that was the case. And concluding, strategic bridges with the important traffic on tanker for trucks, specific studies are necessary, because of assessment and of risk and for the safety security which should be targeted. Storage of flammable materials under bridges should be forbidden, especially for bridges with small vertical clearance. Drainage of bridges should be properly designed. We remember the case of the Matilda Bridge in Rouen, France. The next step is, look at the structured response to fire. There are 2 aspects: performance of concrete and steel, and temperature loads and analysis. We put concrete bridges in the bracket because of the problem of steel steel structures. I mean, less relevant in terms of analysis because those bridges under fire, important fire, just collapse. So let's look at the material, performance of concrete and steel. We used to refer to fire curve as far as fires are concerned. There's a reproduction of what we can find in Promat flyers. And for bridges, this modified hydrocarbon curve. You have below time and the vertical, it's temperature. We can see that the very high temperature doesn't take too much time, to reach the level of 1,000 degrees Celsius. Those who are familiar with tunnels and the aspect, the fire security, safety security of tunnels is, well known. I mean, much more, publication were dedicated to tunnels, and there were significant changes in codes and for guidelines how to deal with this aspect. Because of a series of fires which took place in Europe by the end of this last century. I compare here the bridges and tunnels. So we can see that the curve for bridges is not very different from the one used for tunnels. This is the curve of Rijkswaterstaat developed by the Ministry of Public transportation, I think, in the Netherlands. And in both cases, the fire reached very, very high temperature with a very short period of time in the last 4 hours. So that's the starting point in terms of the temperature. Now, how the material behave. So in case of concrete, the loss of resistance starts at 300 degrees Celsius. With 500 degrees, we've witnessed important creep and deformations. And practical terms, as performance limits is 600 degrees Celsius. The one for the steel and rebar is about 500 degrees Celsius. With, of course, some the laws will start well below. So where these limits are on the fire curve for the bridges, we can see here. So it's well below, what we reach after a few minutes. So in terms of materials, steel and concrete are not very, very, well equipped to resist to fire. That was as far as material is concerned. But you have also another phenomenon. It's a spalling in case of concrete. So you saw the cases with extensive spalling and rebars in the series of examples of fire shown before. And that's how this does look like. There are different types of spalling. It should be underlined. Not here you see, the aggregate core on the surface, explosive, etc. Time of occurrence, nature, violent, splitting, popping, cracking. You can name it. We have everything. It depends of a series of parameters, and that's affect the rebar. It's exposed. So the problem of performance of concrete, it is related basically, how rapidly this spalling occurs and how rapidly the rebar is reached. So the concrete cover becomes a very important parameter in design. Let's show you the mechanism of spalling, which some of you perhaps are aware of the use of polypropylene fibers, which eliminates or reduce, the stress in the section and allows, concrete to survive. The problem of those polypropylene fibers is, they have to be placed then in the section exposed to fire. But when we pour the concrete, it's not necessarily something easy to control. So summarizing the performance limits, concrete, steel, and concrete in terms of spalling is shown here. So there's the world of structural materials we are in as far as fire is concerned in case of bridges. Temperature loss and analysis. I mentioned before, that we use concrete bridges because of, some important aspects, and this is also an element which is considered in the case of tunnels, where this temperature exposure is important, and it's some level where the structure can sustain to the fire loads. And why it's so important, because of nature of the material. Concrete is a very poor heat conductor. So when exposed to fire, very, very high temperatures, we have on the right side, we show, the scale, it's about 1,000 degrees Celsius. The very first layer of concrete, it's very hot, but then it's diminished, and the upper part is cold, basically. So of course, it's function of time, and should be considered everywhere where the structure is exposed to heat. So in the case of concrete girders and slabs, you see on the left side of the picture, all this part is exposed to the high temperature, but not all the element, but just outside. Now, in terms of how does it work, it's going to be shown in a minute. But the effect, generally speaking, of temperature, it depends on structural system, both direction. It's expansion, one, and temperature gradient, the second. This slideshow basically, problem of temperature expansion. And in case of bridge structure, we have obviously two directions to be take care of. Now, as far as gradients is concerned, it's a little bit more complicated, because any hyperstatic structure, behaves differently under temperature exposure. And this is very important because the properties, mechanical physical properties of concrete depend on for temperature. So in any analytical approach, we have considered this parameter. So in terms of time and temperature reach in the material. I mean, in the material, it's not in the whole material, but in material, any part of material, starting where the part is exposed to the heat and going to the part which are less heated. And following this phenomenon, we witness also in case of concrete loss of rigidity. So moment of inertia and thickness are a fact of cracks which appear with time. Capacity, we mentioned the capacity problem of performance limits. So by the end of the process, I use here the structure of tunnels to show where how this analytical approach looks like. And stable, you see the level of temperature on the horizontal line, and characteristics on the left side is face exposure to heat, on the right side is cold zone. So in the analytical approach, with every step, and that's on the left side, with the temperature increase, within an adjustment of the depth of the heat reaching the material, and adjustment in the characteristics in terms of modulus elongation of constant and and each other. So, excuse me. So it's a step-by-step analysis, very time-consuming, to see how, as function of time, the structure performs. So let's summarize my. I'm gonna have more time for eventual questions, and the second part would deal with other aspects, as I mentioned, about 1 month. So you're welcome if any questions arise from this overview.
Okay. Thank you, Stefan, for this nice presentation. Yes, we have two questions. So both of them come from Gulam Nabi. The first one says, how did the Vital-Brücke fire influence the development of fire-resistant design codes for concrete bridges in Europe?
In Europe, that's a good question. I'm sitting here in Montreal, in Canada. So maybe if Nacho, you could perhaps react to this question, but I'm not aware of of any impact. I mean, a very good question, by the way. Thank you very much. It's very, very, very important.
Well, the Eurocodes, they were developed for buildings. So in theory, they cannot be applied to bridges because there is a specific Eurocode for loads on bridges, but they do not talk about fire. So we are using the Eurocodes to consider the evolution of the material properties and the structural models. But for example, the fire loads, they are not included in the Eurocode. So at the end, you can use them as a basis, but we are a little bit lost. So that's why there is so much research and so many research papers published on the topic. So Gulam, I don't know if you want to add something, if you are satisfied with the response. No? Okay, thank you so much. So he says that he gets. Basically, they are they are done for buildings. They do not apply for bridges, but there is a lot of interesting information there that can be useful for analyze bridges vis-a-vis fire hazards. Okay, and then the second question. Okay. Okay, so in line with this, Roberto Cederiña is asking to anyone in the audience, when designing a bridge from scratch and considering performance-based structural fire design, do you have any experience dealing with local authorities as in buildings?
It's a very good question. I mean, bridge fires are not covered by code and standards, and I'm referring here to my North American experience. It's nothing there. So we have some, as you referred to, buildings in Europe. We have the same situation here in North America. It's reflected in case of buildings with some degrees of protection, but we know very well, what's the difference in terms of fire load is between materials in buildings and what is in and high risk vehicle for like tankers. But we there are some cases I was involved in terms of risk, potentially, and it was very surprising to the owner. And we know of some problems experienced by the in case of projects where the firemen were involved on the too late to have any important in the relevant impact on the concept. So the question is very good, and that's the reason also, why we decided to found this task group to make people more, more aware of the problem, and we targeted for guidelines as in our first approach to the product we should be focused on. And that's also the reason why recently we have founded another task group dedicated for the task group 114, which is dedicated to the holistic concept of the project based on fire risk, because there's something, it's completely missing. And I can refer here to one type of construction where it's quite well under control. Those airports. And airports are basically designed, to make sure that this everything is not, the tarmac and the place. No, no, no. It's as far as safety of people is concerned and the ventilation. That's the approach in terms of fire engineering is quite appropriate. But overall speaking, and very recent experiences rely on the risk due to the presence of electric vehicles, buses, especially buses, where the load, fire load is quite important, and those are like not yet properly covered because we are in the learning process. But that's why for the TG114, and we hope to bring something interesting on the market for the overall use of our community and the potential clients to make this more comprehensive and useful in terms of how to approach, because our approach is not very easy. It's not a design like calculating beam for bending. No, it is very complex and very multi-parameter design, and not necessarily structural one. The structure is by the end of the process. It's the risk assessment of risk. Other aspect, safety of people is very important. The most important, safety of people. I didn't talk about safety of people because of bridges, because it's very simple. People are evacuated. They are not there. I mean, they just leave the bridge. The very big problem in terms of tunnels. So any structure is somewhere between bridge and tunnel in terms of risk for humans. And that's the very first step in terms of approaching the concept, and in terms of this multi-parametrical design. It's quite I mean, it's not something you learn in the university. In my time, it was nothing. I mean, I don't know today, but it looks like, it's still, for a little bit tabula rasa. We have to feel with our experience in time.
Okay, so let me ask something for Roberto. He was asking about any experience with local authorities. Once we got a request to assess the fire resistance of a bridge, composite steel concrete bridge outside of Spain. And the terms of reference just didn't make any sense because they wanted to verify the safety of the bridge considering the standard fire, the ISO curve, but this is a cellulosic fire, so it is expected to be useful for buildings, but not for bridges. And then please leave that image there. No, the one with the tanker truck from Montebello. Stefan, can you put that back, please? No, no,
Nope,
no.
I lost it.
Yes,
Yeah,
the last.
sorry.
So they wanted to apply the cellulosic fire instead of the hydrocarbon fire. And then secondly, they wanted to apply this fire load to all the bridge girders and constantly along all the girder lengths. And this doesn't make any sense because if you remember the image of the Montebello bridge fire, you always have a peak of temperature right above the fire. And then the temperatures decrease as you get away from the origin of the fire. So at the end, we said that this kind of requirement didn't make any sense, that a proper performance-based design should be done, and they never replied. So that was our experience. Then we have a question also from McGill, Lakabath Chandraskes. Sorry for my pronunciation, Chandraskar. He's asking about the post-fire damage assessment techniques. So, Stefan, do you want to comment something on this?
I maybe let you perhaps react to this because you've been involved in series of investigations and assessment post fire. I mean.
Yes, so there is not a lot of knowledge on this, especially from the part of the authorities, because structural fire engineering is not taught at the universities or at most of the universities. So the people, they don't know too much knowledge about this. So very often they are very conservative and they would say, okay, let's demolish this, but if you do additional studies, maybe you can save most of the structure and then you can save time to the recovery phase. And this is very important, as Stefan was pointing out for the case of the bridge in California, the MacArthur Maze. So, for example, we did an assessment in Valencia of a bridge that got a fire. It was also a composite steel concrete bridge. I will upload or put the reference of the paper that we published. And in this case, we got some concrete core, we got some cores from the concrete, and we did some tests to check the residual strength of the concrete. We also took some specimens of the steel to see the residual strength and also to check for the ductility. So even if the steel had reached temperatures above 600 degrees, it still had the ductility required for the codes. We also did some laser scanning in order to check for the deformations, because maybe you don't see the deformations very clearly, but you can have some small web buckling or flange buckling, and with this 3D laser scanning you can get that pretty well. What else? Tenacity, this kind of tests. And it is also very important to try to collect all the evidence from the incident and then try to reproduce the incident with numerical models. So you typically use a numerical model to reproduce the fire, then another model, and this model provides you the heat fluxes affecting the structure. Then you use a thermal model to transform these heat fluxes in temperatures within the bridge. And then finally, you do the structural analysis to see if the bridge is able to withstand or not. And in this case of the Valencia fire, we also did at the end a load test. And the results proved that the deflections were in agreement with what was expected according to a linear elastic analysis. So the material, everything was working pretty well. I don't know if you want to add something or anybody wants to add something. Okay. Okay. So Roberto is pointing out that they had an experience in an airport, and he says that it doesn't make sense to do this kind of uniform temperature analysis. I mean, this is what we have. Okay, then we have another person asking, and he or she is asking, or she says that every type of concrete has a different fire resistance. In the Netherlands, there were a lot of tests done by RWS. And do you have any information about this, Stefan?
Testing in the Netherlands? No.
No. I mean, there is a lot of bibliographic studies or reference
Yeah, but
studies.
that's for sure, because as far as concrete is concerned, we know, starting from the resistance, from the type of concrete you use for different for projects, in terms of contact with water, for example, contact with the chemicals, aggressive, etc., etc. So I think we have 5, 10 in North America types of concrete, and depending just types, not in terms of resistance or any other component which could be put in inside. So the of course this parameters define also the behavior in terms of, but it doesn't make any huge difference, because the concrete remains concrete, and the spalling remains spalling in terms of, could be for rapid or less rapid, but I mean the problem is there.
Okay.
And we have also, still referred to the fire load. It's very important to consider what kind of combustible load we have in front of us, because in the case of bridges, the risks are not with the small associated with the small cars. It's problem, the tankers and gasoline, ethanol, whatever chemicals transported on the roads. We don't have them in most of tunnels, for example, but the bridges are, I mean, construction where the risk of exposure to those materials is huge, and that's why the risk are very different. And any variation in some parameters as far as material is concerned, or kinds of protection or whatever, when we're talking about concrete, it's becomes less relevant. We're not in building, we're few centimeters of concrete protection for columns is enough, to allow for evacuation of people. We're in the world where the fire law it's much more important, and the fire curves we show you, it's something very different from the cellulosic one we have in buildings.
Okay. So I'm just posting the article with the assessment of the bridge in Valencia. Okay, I put it in one of the replies. And we had another question by Gulam Nabi. So the question is, in the aftermath of the Matilde bridge fire, what specific structural weaknesses were identified in the orthotropic steel deck design, and how had these findings influenced current fire-resistant bridge design practices?
We could have, for some details, because our colleague from France was involved in the assessment of the security of this bridge after the fire. So we can provide you with, give us your email address, so we can find something and share with you what was and how that could have effect. But from another perspective, I think the exposure to the whatever the geometry and the form of the steel structure is, exposure with this type of temperature, this type of amount of heat is which is tremendous. So that's important. Now I would say what's also can play with it's the release of heat by the structure itself, in terms of how can evacuate? What are the ventilation conditions? Are the winds or not? Are they, all these parameters play the role. But by the end of the process, it's important to see and to look at what it's after the fire. How certain parameters did affect or didn't affect, the development of fire and the performance of the structure. It's another aspect. But if you are still interested, so we can perhaps share with you this information from the other source.
Well, this is a very famous case, the Matilde Bridge fire. And the engineers who did the assessment were very generous because they wrote a very good, an excellent paper in the journal of IABSE. I am also posting the link to this paper.
Oh, super.
And they explain all the diagnostic techniques, and the paper got an award from the IABSE as one of the best papers published in the journal. So. And also, I think that after this fire, there was a committee in France, and they did some kind of guidelines for the design of bridges against fire. But the problem is so complex that it is very difficult to try to get some guidelines because it's just too difficult. The models are too complex, and of course, these guidelines are written in French. So I'm sending the links to the two articles also there. So, do you have more questions or no? Stefan, and I have also a question for the community, whoever wants to ask. So we very often say we shouldn't put anything under the bridge, but still we see fires and fires happening because somebody stored materials under the bridges. What should we do? Because it looks like our recommendations do not reach the engineers in charge of the maintenance of the bridges. So do you have any idea?
Yeah, I have a very good idea, and this idea will be brought in terms of pictures in the next presentation, because the best approach is, in my opinion, put this in the project, in the design, and make the proper use of the space. I mean, for parks, for whatever, to avoid any fire risk for the structure above. And I saw parts, for bike paths below. It's very good. I mean, but no parking, for example. We have here in Montreal a huge parking lot. It's not a big, good use for this kind of. So for me, the structure, the design of the structure of the beach should absolutely include also, the space underneath. That's very important.
Okay. Thank you so much, Stefan. I think we are
My
almost,
pleasure.
it's almost 5. Thanks so much for the effort. Thanks so much the audience for coming and for the questions. And we hope to see you in June for the second part. Have a nice rest of the day. Thank you so much.
Thank you, everybody.